So we're gonna talk a little bit about the inverse function and getting the inverse derivative um, in more of a shorthand method. Actually, getting the inverse derivative isn't the hard part. It's understanding why the inverse derivative works the way it works, or the formula for it in the inverse derivative works the way it works, because understanding inverse functions is very difficult in essence. So let me see if I can clear anything up. First of all, a function itself, as we remember, has to pass the vertical line test, right? LE, I think that's right. Forgive me if it's wrong. So vertical line test, which means that a function like this, right? Oh, that's ugly, but still, it's not symmetrical, but still, as you can see, for one x value, right, we have two y values, and that's a no-no. Think of it in essence of a function like but think of the function itself specifying the process of a pizza delivery man delivering pizza, right? And these being two different addresses. It doesn't work. Doesn't know where to go. The function becomes distorted, and I guess you could say it's invalid at that point because it doesn't give one specific y value. So we need a vertical line test, and this, of course, fails it. So a function like x squared, right? That would be y squared. This is y squared. So x squared, right, is a function because we have for every x value only one output of y, right? But we can have, two x values per one output of y, right? For one y. Now, this is a function, again, because it passes the vertical line test. Oh man, I tried to draw a vertical line. You guys get the point. Oh god, jeez, this is horrible. This is a axis. All right. Okay, so this is a function right here. Function equals x squared, right? That's fine. Now, let's talk a little bit more about that. In order for the inverse to exist, the function needs to be 1-to-1. Be 1-to-1. Essentially what you're saying is a function here can, but it's important for it to pass the vertical line test, right? But doesn't necessarily have to pass the horizontal line test. Like this does it. Well, in order for the inverse to exist, it needs to pass both. So both vertical line and the horizontal line test. The reason is because the inverse, well, let's look at an example, right? If I say y equals to x squared plus 3, right? Say 2x squared. We learned from our pre-calculus days that what we do is we interchange the values, right? And so the inverse function gets reflected across the line y equals to x, right? So here's the line y equals to x, right? So you have something going on at this side, right? Well, on the other side, this is not specifying this function. This right here is not specifying this, just an FYI. I'm just writing something hypothetical or arbitrary at this point. So it's reflected on this instance, right? Cool. Across the y equals x line, right? Now, so this would be the function of x. This would be the function inverse of x, right? Another property that the inverse holds is that the domain and range are interchanged. So for the function of x, the domain, we have a domain and we have the range of the function, right? But for the inverse, right? Inverse of function, the domain is the range of the original function, right? So the domain of f1 equals r of f, right? And the domain or the range of f1 equals to domain of f, right? Okay, so they're interchanged. That means that here we had a specification that for the function to exist alone, we need one y value for every x, right? Well, now if we interchange the domain and range, well, that property still has to hold. We need for the function, no matter what function, as long as the function inverse exists or any function, right? We need that particular property to hold, where there is one output or one dependent variable, right? For every independent variable that the function is evaluated at. I don't know if that confused you. Kind of confused myself. Sorry. But anyways, just keep that in mind. There's a property. Always keep that in mind, that it's reflected across y equals to x, and that we have the domain and range of the original function, right, are changed or switched over or interchanged for the inverse function, right? Okay, so those are a few properties. Now let's look at the above equation. Y equals to 2x squared. No, not 2x squared. 2x plus 3. I want to make it linear, right? Oh, it's not erasing. There it goes. Okay. Now, again, we saw for the inverse how? Let me say, so this is a function of x. Function inverse equals to what? We simply just interchange the values, and then we solve for y, right? So we're going to say x minus 3 divided by 2 equals to y. Or this also, we can simplify this. 1/2 x minus 3 over 2 equals to y, right? So initially, and then if we take that, right? So let me go back to this original function here. We take the derivative of this, right? Actually, let me say this better yet. df, right? Our derivative is simply 2. Correct? Well, check it out here. If we take the derivative of the function inverse, that's negative 1 right here, by the way. And by the way, this is an operator. Doesn't mean it's the inverse. I mean, you're not taking... It's just an annotation, by the way. Doesn't mean you actually, you don't actually take that 1 over anything. You don't actually take the inverse of it. Okay, so what's our derivative? Here. 1/2. And as we noticed, and a common property is that these slopes are inverted, right? So we can say safely that, hold on, let me move this down. So that's why. So if we have df of dx at x equals to some point, right? Equals to f prime x, right? F prime x. Well, then we can honestly also say that df of -1 dx, you're going to be evaluating the function of a. X equals the function of a. Because remember, it has to do with the fact that you're interchanging the domain and range. Oh my god, I don't know why I'm doing this. X function of a, right? Okay, so equals to f prime of x -1, right? Okay. Now, given this proof here, this property, saying that they're inverted, right? Well, we can say then that the derivative of the inverse function at x equals to function of a, right, is simply just the inverse of the original derivative at x equals to a. So all you really need to do is just solve for the derivative of the tangent line at that one point and just take its inverse. As simple as that. So if we have maybe an example, 3x squared plus 2x plus 1, I don't know where this is going to go, but we can figure it out, at x equals to, oh god, I don't know, I'm writing so sloppy, and it's not erasing. Sorry, I'm talking kind of low because it's late. At x equals to, say, 2. I have no idea I'm going with this, I'm just making this up. Our df dx equals to, let's see, maybe I shouldn't have done that. 6x plus 2, right? At x equals to 2, so let me see, f of 2 equals to 12 plus 2 equals to 14, right? What we're saying now is that the derivative, or the inverse derivative, is simply 1 over 14. And by the way, if my math is wrong, please forgive me. As long as you get the concept. Right? And let's see if we can figure that out. Let's see if we can prove that. All we have to do is set y equals to take the original function. Oh man, I really screwed this one up. Dy, no, not dy dx. Let's change the variables. X equals to 3y, and we're going to have to solve for y. I don't think we're going to be able to. X minus 1 equals to y, 3y plus 2. Man, I gotta think about this. I can't think about this right now. No, not gonna work. I don't want to do this. Let's just take a basic function, a linear function. Anyways, that should be, this should work for the, oh shoot. That should work. This answer here, 1 over 14, should be the answer. But let's try one more then. Let's make up another one, linear. Example 3. Say 3x plus 5, right? Let's see what happens. Y equals to that. Okay, so if we take dy dx, or df of, just df, right, of the function, so, what's going on? It's simply 3, right? df negative 1 dx should be 1 over 3. And if you solve that, man, that's really simple. That's no fun. But the concept is there and it works. Like, again, it's a really simple process. Just remember that. Remember that rule. What about rule? What about let's try root value. root, say, x minus 1, right? Yeah, let's try that. So y equals to that at x equals to 4, right? Okay, so dy dx equals to what? It's going to be 1/2 x and negative 1/2, right? And then so we said the function f prime of 4 equals to 1/2, right? Times 1 over root 4 equals to 1/2 times 1 over 2, right? Equals to 1/4. Well, then by that theorem, we should say that it should be, it should state or clarify that the derivative inverse should be 4. And let's prove that. Let's see if we can prove that, right? Let's take the original function. I think it was minus 1, right? Yeah. So I'm going to interchange the values. X equals to root y minus 1, x plus 1, right? Equals to root y, or x plus 1 squared equals to y. Now, we said that x equals to 4, right? Actually, we're going to take x equals to 4, the original function, we're going to take f of x instead. So, x equals to 4, that means f of x equals to, at x equals to 4, is to be 2 minus 1 is 1. Right? Okay. So, if we differentiate the function, or the function inverse, right, equals to 2x plus 1 times 1, right, equals that, and that's simply that, times 1. Now, we can now take f prime of x, right, or f prime of 1, sorry, equals to, so we have to take and evaluate it f prime of a, right? Or f of a, which is 1. So 2 times 2 equals to 4. And that's what we got up here. And you can always prove it. So the theorem works. Sorry for going around in circles. I'm doing this on whim. I'm making all this up as I go along. Let's see how much. Oh, 18 minutes. Yeah, perfect. Okay, so I'm going to let this go. Hopefully this helps. If not, I apologize if I confused you anymore. I certainly confused myself to an extent. Have a good night.